as with every class we're going to have, I will definitely record our sessions and make it available in our what do you call it, YouTube channel. All right. So as I was saying, these chapters theory tended to disappear. So we'll start with the first example for chapter 9. We did chapter 8, which is on the applications of linear programming. So that one, not easy to really assess it in a test. Yeah? But this one is interesting. It is possible to assess it in a test. So, however, you might not be necessarily solving anything. All you will need to do is to derive the problem when coming across these problems. I will try to be as explicit as possible because I believe this is the last chapter before our test. So making a point that we go back to the recorded videos, chapter 7 and 9. So this one will be the 9th chapter. It will be the 2nd chapter. Because the other one, the knowledge, is going to be assessed on an assignment. Again, chapter 8. It's going to be based on the assignment. So now, we are having a concept called transportation problem. Transportation problem is similar to the aggregate planning that we did last semester, whereby we had a transport method. We had several methods that were used under aggregate planning, and one of them was a transport method. This is a lot similar to that. Yeah? So, it says the transportation problem deals with distribution of goods from several points. Need to get my comfort first. So, it deals with what? Distribution of goods from several points of supply, which they are also known as origins or sources. 2. So now, from several points of supply to points of demand. 2 points of demand or destinations. We are given capacity, supply is equals to capacity. So of goods at each source, and then we know that sources, you can't go beyond what you have. Even the answer, the sign of equality usually becomes less or equals to again when you are given resources. So you cannot go above your capacity, not unless you buy. And then we are also given capacity of goods at each source, a requirement. Do not forget requirement. We did mention this. Requirement is also called demand. Requirement is also called demand. Okay, so for goods at each destination and the shipping cost per unit from each source to each. So you're also given what? The shipping cost. The shipping cost per unit from each source to each destination. An example is shown below on figure 9, which is this one. And then the objective of such problem is to schedule shipments so that total transportation costs are minimized. That's your objective of this method. We want to the shipment cost, aka transportation cost. We want to lower the transportation cost. Yeah. Most of the time when you are given, let's say you work for, this is a common thing, but most of us will end up doing for Mr. Deliver, take a lot, and so on and so on. These are the things that you can apply when selecting destination to pick up for or to make deliveries for. You can't plan to go to Saffronburg, then and say, I want to go after that to Sebokeng, and realize that you forgot something that was in SW5, yeah, or let's say Valmore. You see that if originally you were to say, I'm going to move from Saffronburg to Balmore, then maybe to Sharpeville, then to Sebokeng. Unlike you say from Sasolburg to Sebokeng, that is approximately 37 kilometers. Then you come back to Balmore, another 20 kilometers. Then you come to the already with wasted petrol and money. You understand? You need to understand that. So transportation cost is one of the reasons why today fuel it's expensive and the food is expensive. Once it's expensive for ShopRite to deliver food to this ShopRite, ultimately the price of the food must be paid by me. Ne- Okay, so at times the production costs are included. We'll see when we get to the problems if they wanna do it like this. I want to keep things as basic as possible to avoid getting myself a headache. Transportation models can also be used when a firm is trying to decide where to locate new facility. Yeah? So do we need to work from Sebokeng or do you want to work from the Vanderbilt Park? This is it helps you when making those decisions. And do not forget that under one of our chapters, let me see. Because I'm confusing you guys between yourselves and the guys about production one. But I don't think you guys are doing this thing of location. We did it together where you are trying to identify the best location and we're looking at factors such as your availability of suppliers, your obviously you cannot look at only your suppliers, you must also look at your customers. How far are they from you, your politics, like with Vanderbilt Park, we all know that our Mfuleni municipality is not looking after our roads, it's not looking after collecting waste. Like there's a lot is lacking. So once you make your decision, you need to always factor those decisions. It's not only about the calculations to make sense, but also like what type of people are you going to attract, the labor force also. You need to factor them inside there. Otherwise, you're going to have issues when you are in a place of let's say 60% uneducated people. You need to know how to, strategize. Before opening a new house, factory or sales office, it is good practice to consider a number of alternative sites. Good financial decision concerning the facility location also attempt to minimize total transportation and production cost for the entire system. Okay? So as part of the financial decisions that you are making, these are one of the stuff that you're gonna do. So linear programming for transportation example. The Executive Furniture Corporation is faced with a transportation problem shown in figure 9.1, which is this one. As you can see, we have supply in a form of your capacity. You have your supply here in the form of capacity, and this is your initial area, né, which is your source. Then you are supplying to different destinations with their demand. Can you oversupply to a customer? One. They only pay for what they have ordered. Imagine I take a lot, you paid something online, then they bring two pair of shoes and they expect you to pay right there on your doorstep. You wouldn't agree. Same apply. So you can't overproduce, you can't oversupply. You must supply the exact number of products. And this is going to help you when we are deriving the constraints for this example. Whenever you are meeting your demand, you must meet it exactly as it is. And also with your capacity, it's rare that you can have over capacity. You have less or equals to the capacity. That it's important to keep in mind as we are formulating the what you call it, linear program problem. Yeah. There are three supply constraints, one for each source, and there are three demand constraints, one at each destination. The decision to be made are number of units to be shipped on each route. So there is one decision variable for each arc or arrow in the network. Let X, all right. So this part now, I'll write it obviously looking at it. Actually, even if I don't look at it, it's easier to make sure that everything's visible. So I must just say let X, okay, let Xij ne, equals to, whereby I is your source and then J is your destination. Not the movie one again. Then we are going to minimize cost again. The object is to minimize cost. Minimize cost. Why? Because we are given the transportation cost. The transportation cost, they are going from one direction, from this to that. Are we clear? They're moving one direction because we are sending material to the customer. Right. So now then we'll start by saying, oops. We'll start by saying, I'm looking at here, okay, because we are minimizing total cost. Then this is my X1. No? My X1 is going to my X1 also. So because of, remember we had I and J. So I is 1 and then J is 1. No? However, that is 5. 5x11 plus, no? What is the figure? 4. X 1 2. See that? Plus 3. X. Where is that? Okay. Come on. Today my laptop, it's not. Maybe it's because of my approach these days. I've changed my approach slightly and I can see it's not working when I teach. Okay, so this is the 4. Yeah? Oh, I'm actually writing all these numbers. Let me try to grab this and put it there because I want this. Actually, I'm making a mistake, man. Let me do this. This one must open a space here. Yeah, like this. I need to be writing on the center. So these are my answers. They cannot sit together with the thing. Yeah. So now I'm starting afresh. So this is a minimize again. Total cost. Ideally, you write this as a long line. Okay. Then you must say equals to. But in this exercise, it is best to divide them. They will help you to even understand the pattern as we are carrying along. So you're going to have 5x 1 plus 4x. Look at that. 1 2. You see that? 1 2 plus 3 3x 1 3. Ideally, this is one formula. You can just say plus. Don't go that other side. Come down here. Then you go to the other one, which is 8. X, this is 2. Do you see that? 2 1. Because 2 is able to go to 1 there. Plus 4x 2 2 plus 3x 2 3. So you plus there. Okay. Then we are on that one. So it's going to be 9x 3 1 plus 7x 3 2 plus 5x 3 3. Right. Subject 2. Subject 2. Subject 2. Meeting this constraint. Right? So when we're doing the constraints, we are kind of starting afresh everything that we have done on the first section. So we're going to say, now looking at this figure, we cannot exceed this figure. No? When you are supplying, you cannot oversupply. So, because that is your material you are willing to minimize also. Understand? So you can't, when you are minimizing this material, then you say its constraint is greater or equals to. No, you're trying to minimize so that you can find the best low cost as far as possible. Then we're going to have it as x 1 1 plus, which is this one. Then now we're going there. X 1 2 plus x 1 3. It's less or equals to 100. X 2 1 plus x 2 2 plus x 2 3 less or equals to 300. X 3 1 plus x 3 2 plus x 3 3 greater or equals to 300. So now how much are we now supplying specifically the demand? The demand must always be equals to its requirement, because these are requirements. Yeah? So they are equals to. Then things will slightly change now. Demand. Where is demand receiving its products? It's receiving them from 1, 2, and 3. So the when you look at it, this is that, this is that, this is that. So you're looking at it from this point, ne? But you do not forget that we still have I, J. Ne? You don't forget that we still have IJ. Then the whole concept now slightly changes to X 1 1. Okay? Plus X 2 1. You see that? X 2 1. We're no longer looking at it from this point where we are going forward. No, we're looking at it from this point now. X 2 1 plus X 3 1. So this guy is receiving from 3 different points. He wants to receive a demand of 300. You understand? Exactly 300. You cannot say less or equals to because it is some of them. Understand? Greater or equals to, you can't say that. You must not say equals to 300. So this destination has received, you understand, has received precisely 300 products from 3 different suppliers or sources. However, when we are supplying them now, we can have we have our maximum limit. Ne? We can supply less, ne? And but also be considerate that we cannot exceed what we are having there. Okay, then it continues. It's going to be 1 no 1 2 1 2. You see that? Plus 2 2 plus 2 3 2 equals to, all right, I like saying let xij here is equals to, obviously I is S and then J is demand. Okay, then okay, X 1 3 plus X 2 3 plus X 3 3 equals to 200. And all this xij can should be on the first Cartesian plane. Okay? Guess what, guys? Once you have this, you're done with it. You understand? You can't solve this. You understand? You can't solve it in a text because we solve it using a software. However, this is what I would want, constraints only. Yes. Okay. Let me when I'm running my recording, it's fine. I'll erase them. I'll erase them for you, my friend. I want to confirm if I'm still recording. Yeah, it's counting 24 minutes. Okay, fine. So now, we want to supply 100 units. We want to supply 100 units to 3 different destinations. You get my point? And we can't over supply also. We can undersupply, but we can't oversupply. So now we are having, imagine that this is x1, okay? x1, let's not say x1, let's rather say 1. This is destination, or this is I. 1, J, 1. I, 2, J, 2. I, 3, J, 3. Ne? So now from I1, we want to supply J1, J2, J3. You understand? So now we're writing it in this way. We say that is X. Okay? Because we did say let Xij equals to these destinations. Okay? So 1. This one is already, when we say 1, we're meaning we are coming from this source. We are going to that source. This is I here, and then that is J. So I going to this source. Now we want to say I going to that source. Yeah? So it's going to be plus x1. Again, we're coming from there. x1 going to 2. You see that? Then plus x1 going to 3, which is this one. So 3. This is what we are willing to give them. You understand? That is what we are willing to give them. So now, because of, look, we are supplying it into 3 different segments. We are not sure how much each we are giving also at this point. We know that we are giving them 100. It could be below, but it should never be above. Because why? We are trying to minimize the cost. If you're going above, you are maximizing now. So we're trying to minimize the cost. So now that is why the sign is, it's less or equals. Okay. Then now we are moving to this guy. X2. He's going to, he's going to 1. You see that? Then now x2 is going to 2 plus x2 2 plus x2 3 less or equals to 300. Now I'm gonna cruise until x3 1 plus x3 2 plus x3 3. Yes, maximum of 300, yes, but less or equals to, because once he's supplying all 3 of them, so he's not sure each how much is he gonna get. Yeah, he's supplying all three destination. Now we are looking at it from a different point of view. Now from the receiver point of view, remember you have placed orders, demand. These are your orders. You have placed orders. If you said you want 300, you must receive how much? 300. No excuses. You cannot pay more than that or less than that unless there is an addendum. So when material delivered is short, always it is supplied with addendum, because usually your suppliers will say I've inventory on what? On hand. It goes back to the concept that we've already did. When you have inventory on hand, you can immediately supply it. You'll see it almost on your first year of you placing orders, that if your client or your supplier has something on hand, they'll immediately, then they create an addendum invoice to say, we've already given you this much, we're going to give you the other segment. But he can't go beyond that. Also, he has to, at the end of the day, give you precisely what you want. Okay, then now X now. This guy is receiving from, remember ij, it still sits like this. Ij is going to be 1 1 plus this now it's going to 2 2 1. You see that? 2 1 plus wait, let me fix it, sorry. Plus x 2 1. It doesn't change. Then plus x 3 1. Now this guy is receiving from here, is receiving from there, is receiving from there. Do you see that? And then that's why we are saying he has to receive a total of 300, and he doesn't care. Your client will always expect. Now we are moving to this guy. 1 2. Help, guys. One, 2 plus 2 2 plus 3 2 equals to 200. Okay. X 1 3 plus x 2 3 plus x 3 3 equals to 200. Then xj, xij must be on the first because we're dealing with only positive figures. Then we're putting it on the software. We put our constraints on the software. They're going to look like this. That's why I say here you won't be expected to solve anything. It's a linear programming. How many constraints? How many constraints? You go here, you count 1 2 3 4 5 6. Then going across 1 2 3. 3 variables, 6 constraints. We are minimizing cost. Click OK. Then you're gonna get that. Okay. Actually, you must have this number of variables. Actually, your variables are 1 2 3 4 5 6 7 8 9. There are 9 variables. Let's go back there. Linear programming, 9 variables and 6 constraints. Click minimize. Okay. Right. Now x 1 1, x 1 2, x 1 3, x 2 1, x 2 2, x 2 3, x 3 1, x 32, x 33. Okay, then under you minimize, you have 5 4 3 8 4 3 9 7 and 5. Okay, then here you have, you go across x1 1, you have 1 1 1, ne? Then you can just do all of them. X2, you see, for a constraint 2, x2 you have 2 1 1 1 1. Then you go down under x3, you have x3, you have 3 1 1 1 1. Okay, then here you have, okay, x1 here, and you want to skip x22 there, x32, right? Then this one you have x12 1 2, you have x22, you have x33. Then this one you have x13, then you have x23, and you have x33. Then obviously now we're dealing with the equal signs. We're dealing with the equal signs. These ones are less or equals to, less or equals to, less or equals to, less or equals to, and these ones are equals to, these ones are equals to, this one is equals to. You can tell that this is tiring. So luckily it's not in your tests. I can't access a software in a manual written test. It's not possible. 3 4, and then 300 again, then 200 200, expand and solve. And then it says the solution is 100. The solution is 100. Let's see what are they finding. It says the solution is 100. I think I might have omitted their solution. Why am I getting 200? Okay, maybe I might have made a mistake because the solution is this one, 22. Okay, I believe I might have made a mistake somewhere. You will refer to the book. You will do as according to the book, yeah? But that is just for personal reading. It's not important. Okay, now we're moving to the assignment problem. Man. How did I solve? How do I answer this? 1 2 2 2. Okay, nice, fine, it is fine. So now we are going to the assignment problem. Assignment problem. Remember, you won't be required, it's in the record, you won't be required to solve this. You just are expected to give me the constraints, right? So the assignment problems refers to class LP problem that involve determining the most efficient assignment of people to projects. Ne? So it's when you assign, so you assign using the transportation model. Ne? An assignment problem is equivalent to a transportation problem with each supply and demand equals to 1. Ne? So this one was LP model for transportation problems. Ne? The terms are very important. In a test, this is what I mostly teach. Ne? In a test, this is what I ask. Use the LP model for transportation problem, or use the assigning. The LP problem for assigning. Ne? For the assignment. So they say now the assignment problem refers to the class of LP. It is still a linear programming problem that involves determining the most efficient assignment of people to projects, sales people to territories, auditors to companies, for audits contracts to bidders, job to machines, heavy equipment such as cranes to construction jobs. You see that? So the objective is most often minimize total cost or total time of performing the task at hand. One important characteristic of assignment problem is that only one job or worker is assigned to one machine. See that? One job or worker is assigned to. Then 9.2 provides a network representation of an assignment problem. Notice that this network is very similar to the network of transportation problem. In fact, an assignment problem may be viewed as special type of transportation, special type of transportation problem in which the supply at each source and demand at each destination must be equal to 1. Each person may only be assigned to one job or project, and each job needs one person. Adams is the source. Then you assign them to the project. Ne? So you want to see the best possible assignment. Ne? One best possible combination that will yield low cost. So we minimize cost. Minimize cost. Then we are going to say for x11, what is the cost? It's 11, okay? Plus 14, x14 plus 6, x 14 yang yan guys. 1, 2. Then x 1, 3. I said we have the plus, but we go under because we want to understand the pattern. The reason why we go under, we want to understand the pattern. If you want, you can, but it's not advisable. You won't understand the pattern now if you change that. This is 8x. This is 2. Yes, plus 10x to 2 plus 11x to 3 plus, and we're going down there, 9x 3 1 plus x 3 2, but we need a figure which is 12 plus 7 x 3 3. Okay, sharp. Then subject 2 again, subject 2. Here let xij equals 2, whereby I is your source, then j is your demand. Then these are your constraints now. So now remember, you cannot go overboard by providing more resources. Also, you need to be less or equals to when it comes to resource. That function doesn't change. X 1 2, x 1 3, greater or equals to 1. So x 1 1, x 1 2, x 1 3, x 2 1 plus x 2 2 plus x 2 3 1, x 3 1 plus x 3 2 plus x 3 3. Then things are slightly starting to take a different shape. Now we go to x11, x11 plus, now we're going to 2 again, x is it 2 1 plus x 3 1 equals 2. You cannot less, or this is equals to 1. Ooh. Then x, we are at 2 1 plus x 2 okay, 2 2 plus x 2 3 equals to 1 x. So it's more of opposite of that. Wait, why won't I say it? Opposite of that. 1 2, then 2 2, then 3 2. Opposite of that. So if you do it as opposite, you'll see it. So 1 3, isn't it? 1 3 plus x 2 3 again plus x 3 3 equals to 1. Then ij greater or equals to 0. Then you compute it in your software QM, and there are my constraints there: 2 3 2 2 2 1 1 3 1 2 1 1. Done. Then there's another interesting one now. So yeah, we are there now. So now on this one, it's a transshipment. Ne? So in a transportation problem, if the items being transported must go through intermediate point, they must go to if it's an if it's an if statement. Yeah. If your items must go through an intermediate point called a transshipment point before reaching final destination, the problem is now called a transshipment problem. But they are nice rules that they use. They are different that these rules are they're there in test. That's part of the theory. Say, define transshipment problem. Then you give me this rule, isn't it? I think yeah. There's a lot of there are the theory in a form of definitions. Okay, for example, a company might manufacture a product at several factories to be shipped to a set of regional distribution centers. From these centers, the items are where's the statement that continues here? Are shipped to retail outlets that are the final destination. Ne? Provides a network representation of a transshipment problem. In this example, there are two sources, transshipment points and three final distribution points. All right. So now my costs are there. My costs are there. I'm trying to write my cost there. It says Toronto and Chicago. Ne? That could be my X1. 1, 3. It's gonna confuse you. Rather, you copy it here. This, you see that? The 4. I refer to your books, guys. I want to share this. Okay, let me think. I'm gonna move this thing up. Yeah. Okay, guys, this is recorded. In a recording, it will be crystal clear. So here is 4. Then from Toronto to Chicago, it's your 4. From Toronto to Buffalo, it's your 7. From da, 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 da. Okay, New York City. Okay, all right, it's fine. Let me come. Or from Chicago now to New York, it's 6. From Chicago to akemzansi mo kuphela indaba this one to phela indaba it's 4. And then the other source St. Louis no okay, the other one get 3 and then get 4. Okay. I said get 3 and then get 4. Okay. Then from Buffalo, guys, from Buffalo it's 2, 3, 4. Oh, this one is 5. Actually, I wanna 5. Okay. And then 2, 3, 4. Okay. Two, 3, 4. Yeah. Okay. Obviously, let X, I, and J equals to Yebo. We have K 5 and 7. 5 and 7. Thanks, Romeo. Okay. Let this equals to I is equals to source and then end. J is equals to destination. Okay. Then minimize equals to so 4x1 to what? To 3, right? Plus 7x1 to what? To 4 plus 5x2 to 3 plus 7x2 4. Come underneath here. X 3 to what? To 5 plus the number first, which is 6, then 3x 3 to what? To 6 plus the number 2 x3 7. You can see the pattern already. Then x the number first, which is I see 3 x and then 4 5 plus this is a 3. Okay. Whoa. Okay, I think this is a 2 going there, then there's a 3 here. 2 then 3 x 4 6 plus the number, I think it's a 4 x 4 7. Right, then that's your minimizing of cost. Subject to the subject to, I'm gonna take this guy and move him away. Move away right now. Okay. X 1 3 plus x 1 4 800. Right, one again. Ready, judge. We're seeing it again. Right. Then x 2 3 plus x 2 4 greater or equals to 700. The next part, they do it later. Ne? In the book example, does it make sense to do it later? You won't understand what you're doing if you're doing it later. It is best to do it now. So to see it carefully. Then it's kind of starting afresh. It's a middle point. Whatever I'm receiving from x1 3, x1 4, I'm going to distribute it from x3 to 5, x3 to 6, x3 to 7. You see that? So I better write that now. The book is not doing that. Me, I'm like, do it there. X 1 3 plus x 1 4, it's equals to x3 going to 5 plus x3 going to 6 plus x3 going to 7. Then you do it for x1 2. Yeah. x 2 3 plus x 2 4 equals to x 4 going to 5 plus x4 going to 6 plus x4 going to 7. And now we're gonna do what we did on the other one, whereby we are the demand. We need to meet the demand now. We are trying to satisfy their demand. We will say okay, so yeah, there's a tendency of being naughty. So this demand receives from that and that. We're not saying this guy is supplying 1 2 3. We're saying this demand is receiving from 2 locations. You see that? So now is x 3 5 3 5 plus x 4 5. Ya rata leo now. Mixanyana, hey guys, I really do, guys. You need to understand this thing's a child, even for us. Then, so x, I think it's okay. If I go back there and say receive from there, it makes life a little bit better if you're looking it from that point of view. So it's x3 6. Do you see that? Plus x4 6 equals to 350. Then you come here. You can see that it's x 3 3 7 plus x 4 7 equals to 300. Then x, let j must be on that. Then obviously you'll be checking them out. Here they are. You'll be checking them out there. So as you can see, they took these guys there at the bottom, and then I don't agree, because you'll forget. Me, if you start with those ones, then you punch this into your I can't sell one out. So the next concept, yes sir. Repeat. Remember that one of this example. I don't want to think about it right now. My mind will go crazy. Let's see if we'll come across it, a problem similar to that in the problems on Friday. Then we'll solve it based on that. If we don't get something similar to that, alright guys, now I'm not Einstein. I'll never give you something that I can't solve myself. On a serious note. If I haven't seen it, Lena, I can't give it in a test. No. So I'm not here to play games. I'm not here to trick anyone. You must always know, if you fail, Paranik has tried everything in his power to save you. And we're unsavable. Ne? Yeah. Me, I'll always try my best. So, the transportation algorithm is an iterative procedure in which a solution transportation problem is found. Now, we're no longer mixing transportation with LP. We're now doing it as the concept of the aggregated planning. Now we're looking at it as a transportation algorithm, exactly as we did in aggregated planning. So now, transportation algorithm is an iterative procedure in which a solution to a transportation problem is found and evaluated using special procedure to determine whether the solution is optimal. Iterative. Hey, you only understand it when you get to advanced, whereby we say how many iterative are you supposed to conduct when you are trying to meet a certain simulation. So it's more like replication. How many times can I run a simulation? Not how long, but how many times. You understand? Maybe we'll say 1 million times in order for you to get your solution. At the moment you say 1 million times, from experience, that's why computers crash. Then now, remember there was an example in supply chain that we did, whereby we wanted to see how much sales are we supposed to increase to meet our profit. So at first we were using an iterative procedure basically, whereby we're doing trial and error until yes. So this one also uses trial and error. And in now running, I've never asked you to do trial and error in your test, your initial test. We can speak something in the last test. So this example is as good as not coming in the test. However, I agree we are rating cars. Somebody is going to fake their sickness at test 1. So it won't be there at test 1. But I'm not making any promises at test the last one. Again, we're writing tests. Well, I'm writing a minimum of 2 tests. Again, test 1 and test 2. However, I do not have a makeup test, so I have a 3rd test, which is optional. I take 2 of the best. Again, then on that one, I'll plead with the university to say, I need more hours, probably 3 hours, because it's going to comprise of a lot of things. You understand? Because there's no theory or even calculations that are dedicated for that. We are designed to have test 1 and test 2. If you come on the test 3, I give you combination of everything that we are covered. They never exempt for you. So in simple terms, in record, don't get sick for test 1. Collect marks as far as possible. Because also I'm not allowed to repeat questions. That's why I'm forced to give you this example at test 3. You understand? The moderator will say you are repeating. I'm not supposed to repeat. So now, because of the iterative, it became a reason why I slept around 2 o'clock today in the evening. So it is not optimal. A new solution is generated. If it is not, whatever that you're doing, if it's not optimal, a new solution is what? Is generated. So meaning you do it again. This new solution is at least as good as the previous one, and is usually better. This new solution is then evaluated. If it is not optimal, another solution is generated. Not unless I'm able to get questions that don't have a lot of iterations, then we can talk. But otherwise, I don't trust this. We'll see with problems. Yeah? When we get to problems. Because you're not straightforward. You've done this. However, it's the iterations that are a problem. If I can get problems that are within at least 2 iterations, like you do it for the first time, then you improve it, then you get the optimum solution, then okay, we can talk. But I don't want something that will be done 4 times, like in this example. We will illustrate this process using the executive furniture. So basically, my final thing, whether it's in a test 1 or test 2, test 3. It's gonna come Friday. When we are doing the calculations, I'll see what form of calculations they're giving us. But to me, it kept me awake at night. So now, the executive furniture corporation example shown in figure 9.1. Oh, 9.1. Where's 9.1? 9.1. So based on this problem, so in which a solution to okay, this is present again in a special form in table 2. In table 9.2, which is this enemy that you know again. Yeah, right. We see in table 9.2 that the total factory supply available is exactly equal to the total warehouse demand. When this situation is equal to demand and supply occurs, something that is rather unusual in real life, a balanced problem is to exist. A balanced problem is said to exist. So this is a balanced problem. No? And they're saying that it's unheard of. Later in this chapter, we take a look at how to deal with unbalanced problems, namely those in which destination requirements may be greater than or less than original capacities. Then you read there, balance supply and demand occurs when total demand equals to total supply, which was based on the problems that we have covered in that module. Okay, so developing this, né? I don't know if the method is northwest corner rule. Northwest corner rule. Northwest corner rule. I won't read much on this. Let's rather go here. If we still remember. Here is demand. And then this is supply. On the first column, where do we start supplying? What was the where do we start supplying? Still remember? Lowest cost. So this guy, lowest cost, 5. We start supplying. We are trying to meet range. How much do we have? We have 100. You place your 100 there. Ne? You place the whole 100 there. $100. Have we met the 300? We have. Then we go which is what? 8. Yeah? Then how much are we going to take the whole 300 here? How much are we taking? 200. Okay? 200. We are remaining with 100 again. So 100 we can just put it there and make a star. For argument's sake, make a star. Ne? So that you show that we haven't yet placed it. Because if this 100 as we're placing there is not the lowest cost, we still need to move it away. Or you can someone maybe write it on the side. You must find a creative way so that you remember. Okay? Then luckily this is the lowest cost. Okay? Second lowest cost, because this one is ended obviously. We no longer have 100 is gone. Then now lowest cost is this one. So but here we have 300. So we're going to only take 100. Then we take that. So obviously now we are considering it. Okay, then we are left with 200. Oh, we're left with 200. Okay, and that 200 is eventually what we need. It's balanced. Okay, then the total cost now is done by adding everything. Hundred times 5 plus 200 times 8 plus 100 times 4 plus 100 times 7 plus 200 times 5 equals 2. How much is it? I was hoping to find the answer then write it so that we can move along. 100 times 5 plus 200 times 8 plus 100 times 4 plus 100 times 7 plus 200 times 5. I'm getting 4,200. The method that we are doing is called stepping stone. Yeah. Oh. Stepping stone. Aye. So now it's all about occupied shipping routes, squares. Number of rows plus number of columns minus 1. So now 5, 3 plus 3 minus 1. How much is that? That is 5. Okay. So, wait, I'm not going to read this. What I will do, I will take you through the steps. Because I've done the reading. You can tell the story, guys. Look at that. I know. I guess that's why I go and spend the entire night. And the classes, guys, the classes this year. I have a class on Friday and another one on Monday. What does that mean? It means no more PE for me. I must practice. And you know what? You know what's the saddest part? We're not the only people I teach on Friday. I have a 6 o'clock class that goes until 10 o'clock. Yeah, literally. Then obviously, Tuesday, Friday, then I must forget about it. Then after that, I start practicing whatever that is for you guys. If it's a slide, I have to prepare a slide. If it's a chapter, I have to prepare a chapter. Saturday, Sunday, Monday, I must come and deliver it. And not all of them are easy. So now, with this method now, we are trying to say, if you must always start with this, the empty block, start with the one at the top there, which is this one. So we're saying plus here, we're going that direction. We say negative here, then we say plus here, then we come back here. We say negative. Okay, we're trying to derive and yeah, definitely. So it won't change. So what it happens is wherever you start, that's your plus. We are adding only costs. Where you started, that's your plus. Yeah? So the method here, we are evaluating this, which is D, and Boston. So it's going to be represented in this manner. Des B. So now it's equals to So now we want to see if we're saying 4, which is a plus, minus 5 plus 8 minus 4. I want to move. Sometimes I miss my mouse, but the mouse is always acting up. Minus, you said 4, ne? It's equals to. The aim, this value that we are trying to do, the cost factor must go down. We will take the lowest, we will adjust everything based on the lowest cost. Ne? So now 4 minus 5 plus 8 minus 4, we're getting 3. 3, it means that this one is increasing the cost. We cannot consider it. Then we move to another location. We're going to erase now. Now, so we come here. We are now Cleveland Lingi. So it's dash, because we are saying from dash to Cleveland. Dash to Cleveland. If this one is positive, then where are we having our nearest supply of material? It's here. So we're going to have a negative here, ne? And a positive here, ne? Then look, for this example, we have a negative here, then we are going down, a positive here and a negative here. So we're no longer moving that direction that we came with. We've changed slightly path. It's going here, it's going here, going there. It doesn't make sense to just come here and go up. We need to follow the occupied spaces. I will try by all means. I agree the thing for it. I haven't yet seen the problem. I'm still following the example. I haven't yet explored them. That's why we are conditioned for it. If the problems are making sense, then we can easily say we'll figure out one that don't require many arguments and then can be one. Otherwise, yeah. For now, I haven't yet explored all the possibilities. I'm still taking it at face value. So now this is 3 minus 5 plus 8 minus 4. The spacing, maybe it's a pen. My pen is too thick. I want to reduce my pen size. But it's fine. Okay. Minus, it's plus 7 minus 5. 3 minus 5 plus 8 minus 4 plus 7 minus 5. Hey, the cost is increasing. Okay, where is our others opening? We erase. I was thinking about a digital pen. It's irritating. I got irritated last night. I was like, what is this? And apparently, there's something that people are not being taught. Ne? That is supposed to be made knowledge from here to the other techniques 3 if we taken. So I haven't yet received anything lurking, any communication from the module lecturer. And it's difficult for me to know where I'm supposed to stop or continue and stuff like that, or what is it that I must emphasize. So it seems like I must go to him and say, but now I'm still new, I'm under pressure. Every night I'm practicing. I'm going to create slides for my tomorrow's class. And the next day I need to prepare problems for another class. It's just too much. Like every day I'm busy. You know, where I'm coming from, I was not working as much as I am here. Have you worked Monday to Sunday, like with no shame? When I get home, I open my laptop, I work. So now we're going to start from this guy, FA. Ne? We still have this one we haven't explored. Ne? So let's see. FA is equals to, so FA one more no simple, plus minus plus minus. Straightforward again. So FA, so that is 9 minus 7 plus 4 minus 8. 9 minus 7 plus 4 minus 8. This is what we are looking for. This is what we are looking for. When we are saying costs are going down, and then we're going to follow that. But because of, for the sake of the example, we want to still test in C. And this is why I say, sure, me, I was angry last night as I was doing this. So EC, we have 3, at least it's going close by. So that's our negative now. That is our positive negative. So 3 minus 4 plus 7 minus 5. Then we want to see now 3 minus 4 plus 7 minus 5, which is 1. So you are increasing by positive 1. So we're going to now follow F1. So now, when we are following F1, we realize that there was a positive here, there must be a value here, there must be a negative value here, there must be a positive value here, and there must be a negative value here. The adjustments that we're doing keeping in mind that we're doing them keeping in mind that 300 must always be satisfied. Understand? So how much can we remove this side? How much can we remove this side, ne? And still remain with 300? So let's say we remove this. We remove 100, ne? We add here. This one becomes 200. However, this one is a negative, then we give this one 100. Hey, it's erasing stuff now. $100, ne? Then 100. Then erase. There's a white pen. I'll change my pen to be white. Hey, this thing is faint. Yesterday I discovered that I had a white pen. Oh, this chapter, guys, tested me big time. Yo, this one, obvious. When we are here to learn. So that's our new solution. Then now you write. Then now you write now 100 times 5 plus 100 times 8 plus 100 times 9. 200 times 4 plus 200 times 5. Do that quickly. 100 times 5 plus 100 times 8 plus 100 times 9 plus 200 times 4 plus 200 times 5. The solution is 4,000. What happened to the cost? It went down. Hey. Yeah. And now, these guys, they were just explaining the process here. Then there's the solution that we had. Where's the solution? This is the solution that we had. Yeah. And these people to say, do it until we don't get any negative values. Then they wanted to do it again. and that's why I was angry. So I will do it one more time. I cannot do further than this. Then I'm tired. So now they start afresh from here. Have positive minus positive minus, and it's dB equals to 4 minus 5 plus 8 minus 4. 4 minus 5 plus 8 minus 4 equals to 13. This goes extremely high. Okay, then we look at it from this guy. So this one, 3 positive, it goes to 5. Then instead of turning here, it doesn't make sense to turn here. He turns there. You see that? We turn there and we turn here. Then it's going to become DC equals to 3 minus 5 plus 9 minus 5 equals to 3 minus 5 plus 9 minus 5, 2. This is not our solution. Then we come here. This guy has to go there, there, there. So he is EC equals to 3 minus 8 plus 9 minus 5 equals to 3 minus 8 plus 9 minus 5. Oh. I'm getting my -1. Although I still have this one. This one we can just somewhere do it, calculator fast. 7 minus 4 plus 8 minus 9 is 2, is positive. So I think -1 is the best solution. Okay. So positive, negative, positive, negative. Okay, so now if I am to take, let's say, this 100 here, you see this 100, and put it this side, then here I need a 100. No. I need a plus 100 to make it a 200, to make it a 300. So you see now, so we've lost there. So 100 and that's your 100 there. Okay? Then you come this side, you have 100. You see that? And you have your 100. So this is a new solution. Then you are expected to calculate all of them. We are not going to write 100 times 5 plus 200 times 9 plus 200 times 4 plus 100 times 3 plus 100 times 5. And the total cost goes to that. You see 3.9 there. And this is how it looks. Okay, so actually we did it twice, and then on the final one, you see on this final one, they don't have anything above it. You see that? They don't have anything above this one. So what did they find is They found a positive 2 there. No, 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 no. Come on. They found only positive numbers. Yeah, which is 2. Yeah. They found 2. Ne? They found 2. They found 1. They found 1. So obviously it means that we're gonna stick to 3.9. Are we clear, guys? This is what they found. So I'll do only one, which is, if you start here, it's 4, and this negative, you go down here, plus, and you can't turn here, you must turn here, minus here, and you come to, I think, C here, which is positive. So now for B, D equals to DB, I mean, this one. DB is equals to 4 minus 5 plus 9 minus 5 plus 3. 4 minus 5 plus 9 minus 5 plus 3. Then the value becomes 6. Why is it 6? What did they add? They added a minus 4, okay? 4 minus 5 plus 9 minus 5, plus 3. They added the 3. This 3 here. And then they went this direction to minus 4. Ooh. Minus 4. Minus 4. Then the value becomes positive 2. So they've done it twice. They've done the iterative twice. Then that's where they end. If it happens that you can do iteration only once, then it's good for the test. Ne? Yeah. I will see you on Friday. I'll have to apply my mind. It's either I'll have to say to you guys, apply iteration only once. I think that will be fair. Yeah? Yeah, only once. It cannot be twice. Yeah, now it cannot be twice. And hot. Ooh, it's killing me. So now, special situation with transportation algorithm, the unbalanced method. You see that? The unbalanced method. Ne? The unbalanced method. I'm going to put a, look at this, guys. When I use a white pen, okay, I think I let my emotions drive me too much. So now, this is an unbalanced system, ne? So what do we have? 300 here. We have 300 here. So we're trying to meet 300. What's our minimum? Our minimum is 5, again. So we take the whole 250, and we're remaining with 50. So now we have this 300 here. We take only a fifth, then we have 300. We are remaining with 250. Luckily, this is a minimum 1. 250 goes there, but we don't need 250. We need 200. So we are doing what? We are erasing this. Yeah, and then we write it 200. Then we have 50 rand, 50 not rands on hand. So now this one is complete. However, we still need to have this. Then this one we're taking 150. We are remaining with 150. Do you see that? Then you have a dummy. When it's not balancing, then you're gonna have a dummy. Ne? And obviously you do the iterations, which is going to be once. Then moving right along. Now, in this instance, we have, guys, hello? In this instance, we have this situation. We have this situation whereby our totals, ne? You see, we are short of 50 under the supply side. We're short of 50. So it's going to be 200. Then, what is the cost of the new material? They did explain it. Okay, 0, 0, which is fine. Let's rather move here. Let's rather do this. I erase here. So basically, first thing first you did, if you find a problem similar to this, you say 200 plus 175 plus 75. You're getting a 450. That's a 450 there. Then it needs to be balanced. 250 plus 100 plus 150. And then it says 500. So there's an imbalanced situation, right? An imbalanced situation, it needs to balance. So we then add a dummy plant. Previously, we added a dummy warehouse. Now we are adding a dummy plant. Yeah? At cost 0, 0. Then a dummy plant will have a 50 to make it 500, 500. So now we are supplying now 200. We need only from 200, we need 150. We need a 50 to make it a 250. Then we are left with 125. 125. 125 is the least. So we only need 100. So we're gonna transfer 25. 100 transfer 25. Under this one, we need 150. So, however, when you combine from here, 75 plus 25, how much you have? It's 100. You are missing 50. There's your 50 from a dummy plant. Then you have this. Okay? Okay. So the unbalanced and balanced, I'll need to prove if they need to be conducted with that thing. But it's fine for now. So now moving right along. This one is a degeneracy in initial solution. How is it a degeneration now? Yeah. I want to see how is it a degeneration. So now this is 100, the lowest. But the lowest is 7. It's not 8. The lowest is this one. And then Okay, 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 okay. These guys, here they've already run the iteratives because honestly, you know how we're doing it. Again, we always start with 7, so they've done the iteratives here. So I'm gonna skip this part. We have because it will require us to do the iteratives. Just read about it, and then you'll be able to know why did they have 100 there, and so on and so on, because it doesn't really make sense for now. So let's see this one. 815. Okay, what's wrong with this thing? This one also, this is not the same as that. So here you just read. This is during later stages. Degeneracy, degeneracy. These are the concepts that I wouldn't assess honestly. This is out also. Okay, then we have this guy. Oh, this guy is very interesting. With my last 10 minutes, the last thing was the chapter was long, guys. What pissed me off is the fact that I needed to do assignment algorithm, and well, as I was going, this sequencing, I realized that no, it's not changing, it's not adding anything new. Then I had to cancel it. But I had to do it the whole night before. So like, yeah. So here, I omitted certain data. Ne? So now, this exercise, Kian, what method are they using here? Facility location analysis. Facility location analysis. So we are having warehouse. Okay, we are introducing new warehouses, ne? New warehouses. Let's say production plants, which is S. No, guys, you know what? I'm feeling tired. No, no, no. Oh. I can tell that I was gonna do mistakes because now I was no longer reading. Nah, nah, nah. Okay. When we meet Friday, I'll start with this example. Yeah? Because I feel like it's important. It doesn't have complicated things. It's just filling up the table, and you are actually testing two values for time. You are having Seattle and Birmingham. So we'll do this problem before we start problems on Friday. Right, guys? Can we just end it here?